El profesor Jerry Bona es un reconocido e importante investigador norteamericano cuyas investigaciones y profundas contribuciones han tocado diversas áreas. Entre las principales áreas de investigación del profesor Bona se encuentran la mecánica de fluidos, las ecuaciones diferenciales parciales, la matemática computacional y el análisis numérico asociado, la oceanografía, la ingeniería costera, la economía matemática, por mencionar algunas. La trayectoria investigativa del profesor Bona se ve reflejada directamente en toda su actividad académica. En primer lugar, de acuerdo con los registros de la base de datos de MathSciNet, entre el año 72 y 2015, el profesor Bona ha publicado alrededor de 150 artículos en las más prestigiosas revistas internacionales. Sus publicaciones cuentan con alrededor de 3.000 citaciones. De acuerdo con el número de citaciones en MathSciNet, sus publicaciones se encuentran distribuidas en las siguientes áreas: sistemas dinámicos y teoría ergódica, mecánica de fluidos, teoría de juegos, economía, geofísica, análisis global, análisis en variedades, análisis numérico, investigación de operaciones, programación matemática y ecuaciones diferenciales, entre otras. El profesor Bona tiene coautoría con más de 50 destacados investigadores en todo el mundo, algunos de los cuales han tenido o tienen una gran influencia en el área de modelos dispersivos desarrollados en Colombia. Entre estos autores se encuentran los profesores Rafael Iorio, Gustavo Ponce, Marcia Cialon, Jaime Angulo, Felipe Linares, Jean-Claude Sot, entre otros, personas que han formado muchos de los investigadores en esta área en Colombia. El segundo, el profesor Bona ha participado como organizador o coorganizador en cerca de 50 eventos matemáticos alrededor del mundo. Tercero, el profesor Bona ha realizado múltiples visitas en calidad de profesor visitante en más de 45 prestigiosos departamentos de matemática o institutos de investigación alrededor del mundo. Cuarto, el profesor Bona, durante su trayectoria investigativa, ha formado cerca de 30 doctores. Finalmente, quisiera mencionar que el profesor Bona ha participado como editor en más de 40 revistas de gran prestigio e impacto, no solo en ecuaciones diferenciales parciales, sino en áreas como matemáticas aplicadas, computación, análisis numérico, sistemas dinámicos, mecánica de fluidos, entre otras. Con ustedes, el profesor Bona.
Thank you very much for the introduction, Jose. It's a great pleasure to be here, I have to say. I'm coming from a long way, and it was worth every minute of the trip. The hospitality and the warmth are unparalleled, and what I didn't expect is such a beautiful country. I just had no idea. Sorry? Okay, but somebody has to do something about the microphone then. Can you hear now? All right. Okay, so what I was saying was that it was, I came a long way to get here, but it was worth every minute of the trip. The hospitality and the warmth are what you expect of a Latin country, and by the way, it's superb. But I didn't expect such a green country. This is something I just didn't have any idea about. So it's a pleasure to be here. I'm going to talk about, the title was a mystery for a long time because I hadn't figured out what it was. Oh, the number of students that are attending this conference is absolutely amazing. I don't think I've ever been to a conference at this level where you have more than half the participants are students. So this caused me to change my lecture. My lecture is really not the lecture I had originally envisioned. So those of you who already know all of this are free to sleep. Okay, so I'm going to be talking about the work of a lot of people. I think most of them are on the board there, probably not all of them. And I probably won't mention their names as we go, but in case there would be a complaint, there they are. Okay, so I'm going to be talking about water waves. And water waves, it's a complicated subject. We already had the ingredients. This is the water wave problem. We already had the ingredients for this around 1800. So Euler had written the Euler equations, and Bernoulli had understood a model for the free surface, and so we had the ingredients for what you see here. Now let me explain this. Too many things. Okay, so I'm thinking of an ocean with a flat bottom. You get that the same place you get point masses. And here's the free surface up here. And it's three-dimensional in this picture, but I'm going to draw it two-dimensionally because I draw better in 2 dimensions. So here's the bottom. Now, the most important variable, dependent variable in the water wave problem is the following. If you take a point, I'm going to call it xy, on the bottom, and you tell me what the depth is. Okay, that's the depth at the point xy at time t. If you tell me that, I can tell you the rest of it very easily. The rest of it's easy. This is the hard part. And if somebody will just whisper that in your ear, the problem becomes linear. It's still not simple, but it's easier. Now, we don't usually work with this variable. We have an undisturbed depth, like that, and we usually subtract that from this depth. Of course, that has a disadvantage that this new variable, eta, is no longer non-negative. It can be positive or negative, whereas h, of course, is certainly non-negative. Nevertheless, eta can be small. That would be small waves, whereas h, of course, is not going to be small. Okay, so this is the variable we work with, and that's the important variable. If you know what that is, the rest of the problem's easy. Okay, now let's look at these Euler equations, the water wave problem. I've already scaled things. So you see, x and y are the horizontal variables, and they're scaled by a typical wavelength. Okay, so that the wavelength in the scale variables is 1, order 1. On the other hand, z, the vertical coordinate, is scaled by the undisturbed depth, this one. Okay, and then eta, this eta is this important variable, the deviation of the free surface from its rest position, that's scaled by an amplitude parameter, a. And then time, there's only one way to get time, and that's to use the gravity constant. This is the natural way to do that. And phi is the velocity potential. Okay, so those of you who know something will realize that I've already made a lot of assumptions. I've assumed that it's irrotational, incompressible, okay? And those are pretty serious assumptions. Incompressible is not too bad for water. Irrotational's not so easy. Okay, so let's look at these equations. The first equation is Laplace's equation. So that doesn't sound very difficult. Laplace's equation in 3 dimensions. There's a beta here because, oh, I haven't told you what beta is. Okay, there's two parameters that come up automatically. Alpha, which is the amplitude, the typical amplitude divided by the undisturbed depth, and beta, which is the undisturbed depth divided by the wavelength, typical wavelength. Okay, so these are just numbers. They're non-dimensional, they're just numbers. And at the moment, I'm making no assumption about them, but soon I will. Okay, so this is Laplace's equation. That just follows from the fact that it's irrotational and incompressible. Okay, now, if phi is the velocity potential, then the gradient of phi is the velocity. So the gradient of phi is the velocity field. Let's call it u, v, w. So these are the two horizontal velocity vectors. These are the horizontal velocities. That's the vertical. Okay, so what is this condition here at the bottom. The derivative of phi with respect to z is 0. The derivative of phi with respect to z is the vertical velocity. So this is just saying that the water doesn't flow through the bottom, and by the way, there's no water coming up from the bottom either. Okay? These are the Euler equations. For those of you who know a little more, it's not Navier-Stokes. Navier-Stokes, the velocity comes to rest at the bottom, not for the Euler equations. Okay, so that's all simple. It's simple and it's linear. There's really nothing much to it. Everything, the whole, and by the way, there's no time derivative, right? No d by dt. Everything that's interesting occurs here. These are boundary conditions on the surface, and there are two of them. Those of you who know about Laplace's equation will wonder, Laplace's equation normally requires one boundary condition on the whole boundary, and that's it. You don't need any more. But why do I have two? The reason you have two is because the solution involves an unknown domain. So eta is part of the solution, and you don't know that domain. That's part of the solution. Okay, so let's look at these two conditions. This second condition here is actually a very simple condition. This is a piece of the free surface. Okay, so just think of that as this bit right here. Okay, and I'm at a fixed time t0, and then I want to know maybe a microsecond later, where is the free surface going to be? Well, there's two different ways of checking that. One is you can just take the derivative of eta with respect to t, and that'll give you an idea of where it's going. Or you can take the velocity vector, say at that point, and you can take the normal component and the component in the vertical direction, you'll figure it out as well. Those have to agree. If they don't agree, the free surface won't hold together. And that's all this condition says. That's all that is. So that's what's called a kinematic condition. It's just a consistency condition. It's not very complicated. The water wave problem sits here. That's Bernoulli's condition. And I won't go into it because it'd take me too long. But basically what it tells you is that the pressure is continuous across the free surface. And that means, by the way, that there's no surface tension. Okay, so as I say, this is the water wave problem, and it was available in the early 1800s. You had all the ingredients to write what I've just written here. Okay, and you say, well, that's it. All I have to do is solve this kind of equations. This is a very hard problem. This is a problem that people have been grappling with for decades, and we still don't know very much. I mean, there's plenty of open problems of a very simple nature about this set of equations. Okay, so suppose actually a practical issue arose, and you wanted to understand it using a mathematical model. Well, you can't use that. Even today, that's not usually the way people do it. And certainly in the 19th century, they had no chance of understanding this set of equations. All right, so, okay, I've already said all that. This is John Scott Russell. So you won't know John Scott Russell unless you know fluid mechanics. He was not a mathematician. He was kind of an engineer, one of these Victorian figures that did all sorts of things. He did teach mathematics for a year at the University of Edinburgh. I don't know what his qualifications were for that. Okay, so it's April of 1834, and Russell is working for a transportation firm in Scotland. Okay, Scotland in the 1830s. How would you transport goods? Not by horses and wagons. The roads were hopeless about half the year, and the rest of the year they weren't great. You did it on canals, and those canals are still there, by the way. So I'm going to look at a canal. I'm looking from the top, down on the canal. So here's Edinburgh. And over here is Glasgow, excuse me. And this canal is about 80 miles long. something of that order. And as far as we can tell, Russell, who's here, is about 10 miles outside of Edinburgh. Okay, and he's doing something which is interesting, but I won't go into it. And here comes a barge. That's the way you transported goods. And the barge is drawn by a team of 2 horses. Okay, so this is what's happening. And the barge is heavily loaded. It's deep in the water. That's important. And it comes to a sudden stop. Now, Russell, who wrote enormous amounts about what I'm about to tell you, does not say what stopped the barge. I think that's the only thing he didn't say. But probably a tree had fallen into the canal. Anyway, the barge came to a sudden stop. You can do this experiment in your bathtub. You take a Frisbee maybe, you push it, and then you stop. And you'll generate waves. All sorts of waves. That's what happened here. Most of them weren't of any interest, but there was one that moved out. So I'm looking at it from the side. It was just a heap of water. I'm going to show it to you later. And it was uniform across the channel, and it went rolling off down the canal. Okay, now fortunately for us, there was another horse. Russell got on this horse and chased after this wave. And for about 1.5 kilometers or 2 kilometers, what he noticed was that it moved at constant speed and with constant shape. Okay, so those were just his observations, as nearly as you can make observations on a galloping horse. Okay, all right. So Russell was intrigued by this. He went on to do over a period of. There was no funding for science in those days, so actually they did finally get some funding, about 300 pounds, to do some experiments. I'll show you the experiments in a second. So Russell reported bits of this over a period from 1834 to about 1844. In this decade, his work became known, and let me show you the experiments. Oh. Okay, well this is Russell's drawing of the event. Now this is fanciful because he's got 6 horses here, and that's not the case. They were drawn by 2 horses. All right, these are again Russell's drawings. These are some of his experiments. He did all sorts. He built a channel, and one of the experiments he did is to drop a big block into the end, and that generated this wave of constant speed and constant shape, which today we would call a traveling wave, but they didn't in that time. And he did various experiments with this. He reported them in the major report was in 1844, but the work had been coming out over a period of time. So Russell was enamored of this phenomenon. He thought it was important, and he had lots of names for it. He called it the Great Wave of Translation, this thing, or the Primary Wave of First Order. He had other exalted names for it, but the name that stuck was solitary wave. Now, why does he call it a solitary wave? Well, it's all by itself, right? I mean, waves in those days were things like this. These waves have neighbors. That wave doesn't. So it's a solitary wave. Okay, so this was his discovery, and in his long report, he threw out a challenge to the mathematicians. It's quite definite. He said, look, you guys with your theory didn't find this. I found it. You go back to your theory now and find it. It has to be there. Okay, so that was pretty, well, this was 19th century. All right, so the mathematicians of the time took him up on it. So the first one to go after him was Airy, Sir George Airy. Sir George Airy was a major player in science in Britain in the 19th century, and very distinguished man. So Airy, now see, Airy could have use those equations I put up on the board the first slide, the water wave problem. But of course that was hopeless. They didn't have the tools for that kind of thing. So he built a model, a mathematical model. And let me show you the model he built. Okay, maybe I've got it on the slide. Yeah, there's Airy's theory. Now, any of you who actually bothered to go back and read old papers will know that this is not what Airy wrote. I'm looking at what Airy wrote with modernize. With modernize, this is his theory. This is what we call shallow water theory now. So Airy invented that in 1845. So eta is what it was before, and I mean, remember this solitary wave was uniform across the channel, so there were no y derivatives. So the water wave problem simplifies; it becomes one-dimensional horizontally. There's still the vertical variable. So eta is what it was. It's the deviation of the free surface from its rest position, and here's Airy's theory. Yeah, there. All right, so G is the gravity constant. H naught is this undisturbed depth. It starts off like the wave equation, d eta dt plus a constant times d eta dx. And all that says is that everything in sight, not just this special solitary wave, but everything moves with constant speed, root gh naught. But there's a correction term in Airy's theory. It's this one. Okay, so this is just a constant, but this is a quadratic term, eta d eta dx. And this is the simplest hyperbolic conservation law with modernized, but of course this was new in Airy's time. So this is Airy's theory. And if you agree that this is a good model for what Russell was observing, then it's easy to see that there's no solution like that. Because what would it mean to have a solution like that? It would mean that you had a function eta of x and t, which was some function phi of x minus ct, where c is the speed, c is a constant. Okay, this is a traveling wave. That was what Russell saw. Okay, and if you take, probably I have it on a slide, if you take that format and plug it into Airy's equation, you get this. Right? The time derivative becomes minus c times phi prime. You'll notice that here, everything in sight is the derivative of something. This is the derivative of phi, this is the derivative of phi, and this is the derivative of phi squared. So if you put the derivative outside everything in sight, you've got the derivative of some function is 0. So that function is constant. I give this to second-year students even in the USA. And that means it doesn't look like that. Okay, so this was Airy saying that Russell was wrong. And in regard to his experiments, he was saying that, well, he just didn't look carefully enough. If he'd looked more carefully, would have seen. All right, and there were no videotapes at that time, by the way. So, I mean, when you generate a solitary wave in the laboratory, it's absolutely clear that there is one. And if he'd been able to videotape it and send it down to Airy, Airy would have changed his mind. But that wasn't possible. Now, the next person who took him up was Stokes of Stokes' theorem. This is a guy you know. He wasn't, this is a young picture of Stokes. He wasn't at that time Sir George, but later he would be Sir George. Stokes is a major character as well. Stokes took Russell up on his challenge, and he also built a model. I won't go into how they did it. It's interesting, but we don't have time for it. Okay, so here's his model. So it starts off just like Airy, d eta dt plus d eta dx times this constant. But instead of that eta d eta dx term, Stokes had the idea that the wave was small enough that linear theory was going to be good enough. And so the correction that he got was this term, this is a constant, the third derivative of eta. Okay, now, of differential equations that you learned when you're babies, this isn't one of them, right? It's not elliptic, it's not hyperbolic, it's not parabolic. Okay, these days, of course, it's a very popular type of equation, but that's recent. Okay, this is a little more complicated because this does have traveling wave solutions. If you stick this ansatz into here, you get an equation that has solutions, but they don't look like this. They're periodic. Okay, so Stokes went on record as saying, yes, he's wrong, although for a different reason. All right, so these days, if you had a conundrum of that sort in front of the scientific community, it would probably take about 6 months before people would figure out what was going on. But things moved slower in the 19th century, and the person who gets credit for understanding what was wrong with Airy and Stokes in terms of trying to have a model with solitary waves was Korteweg. Korteweg was a Dutch mathematician, there he is, and his PhD student De Vries. I'll show you what they did in a moment, but they settled the issue. They understood where both Airy and Stokes had gone wrong. Now, as is often the case in history, they weren't the first. The first was assuredly Boussinesq. Boussinesq, the French mechanician. So in the 1870s, Boussinesq understood exactly what I'm going to tell you in just a second, and the Korteweg-De Vries paper is 1895. Now, why is it that the equation that I'm going to put up in a second is called the Korteweg-De Vries equation and not the Boussinesq equation? Well, there's a lesson here. The Korteweg-De Vries paper is 15, 16 pages, it's in English, and it's beautifully written. I give it to students today, and they read it without any trouble. The notation is our notation. It hasn't changed. The Boussinesq paper, it's about 700 pages, it's 2 volumes. It's written in French. That's not the problem. He doesn't write very well. Okay, so there's a lesson there for you youngsters. Write well. People will pay attention. All right, so here is the Boussinesq-Korteweg-De Vries theory. And you'll see that it has both the Airy term, this nonlinear term, and this third derivative that Stokes derived, right? It's got both of those terms in it. And that was the point. If you just have nonlinear effects and you don't have this third derivative, which by the way is called dispersive effects, then what will happen to a heap of water is it will just steepen and it will eventually turn over, it'll break. Instead, if you have no nonlinear term and only this dispersive term, then the wave will spread out. You take a heap of water and it just spreads. Okay, so if you have both of those effects in, which is what the Korteweg-De Vries theory has in it, then the steepening and the spreading can balance. And that balance is where the solitary wave lives. So this is an exact solution of the Korteweg-De Vries equation. So let's go back a second. If you stick in a traveling wave assumption, by the way, mathematicians, when they see equations bristling with constants that they don't understand, they get rid of them, they scale them out. Okay, so you can work with the equation in this form. You don't lose any generality. And these are exact solutions. So for any positive value of C, this is an exact traveling wave solution, and that's the solitary wave. Well, so Russell, by the way, was still alive and pleased. Stokes, by the way, admitted in print that he was wrong. Very unusual. Okay, and then this subject, this little teapot tempest, died. There was no further activity in this. Korteweg-De Vries paper appeared, everybody said, okay, fine. And if you look in Lamb's text, which is hydrodynamics. It was the Bible for fluid mechanics for about 100 years. You will not find the Korteweg-de Vries equation. You will find no mention of Korteweg or de Vries. You will find Boussinesq with a footnote. That's all he gets for 700 pages. Actually, the only thing he says about solitary waves is some work of Rayleigh, which I won't go into. Okay, the subject died, and it came back to life in the 50s and the 60s. And I don't have time to trace the history, but the history is fascinating. It's really, truly fascinating. So these equations, by the middle 60s, were something that people were working on, and by about 1980, it was industrial proportions. All right, so let me show you now a few solitary wave or solitary wave type things. The first thing I'm going to show you is the Russell one. These are pictures on the canal that connects Edinburgh to Glasgow. It's our second try to make this wave. Okay, so this is the canal. The first time we had a guy on a horse with a Victorian costume and a top hat, and we were going to take a picture. It was going to be wonderful, but we failed to make the wave. And the reason we failed to make the wave was because we didn't have a barge. We had a motorboat, and we forgot to load it heavily. You need it deep in the water to make this thing. If it's not deep in the water, you won't see anything. So we needed to put a lot of weight in this boat. Now, where do you get a lot of weight, at a conference? Graduate students. So you run this thing at full speed into this part of the canal that we've got nice control of, and then you reverse it, and of course it's not good for the motor, but there you see the wave. This is probably smaller than what Russell saw. Russell says his was about 18 inches, and that's more like 12 inches or something like that. So that's the Russell observation. Now these are solitary type waves. This is on the River Garonne. And if you want to know where the surfing records are set for distance, it's not in the ocean, it's on rivers. 2 or 3 miles. Okay, so this is generated by the tides. The Garonne flows out into the ocean. In the spring and the fall, you have these very high tides. And so the river is flowing this way. And the waves are coming upstream. These are also solitary type waves. Now, you have to be careful. These are internal waves. These are underneath the ocean. They're about half a kilometer down. And the picture you're seeing, the color is artificial. This is from satellite. It's radar. And you're picking up these enormous waves. Let's see. Yeah, you can get an idea how big they are because that's a cloud. That's something the size of this town. There's a sonar picture of what they look like. These are coming in from the deep water off the east coast of the United States. And notice the scale. These have an amplitude of 75 meters. These are meters. It's almost a football field size wave. And the period of the wave, 5 minutes. I mean, these are vast waves. And they're important, by the way. These waves move, not here, but in the South China Sea, they move nutrients around. And if they quit moving the nutrients around, we would have some problems. You also have solitary waves in much smaller scale. This is a fiber optics cable, and I'll say something about that a bit later. This is probably important for the following reason. The way a fiber optics cable works, you generate a signal, and it usually is sine waves, and that goes down the channel, the piece of glass, very special glass, and it begins to come apart because of dispersion. So you have to collect the signal every once in a while, clean it up, and regenerate it. And you'd like to do that as seldom as possible. The less times you have to do it, the better. And it turns out if you propagate the signal as a solitary wave rather than a sine wave, it'll go much further. oh, this is, okay, we won't bother with this. Okay, now, I want to talk, okay, time to do some mathematics. Let's talk about existence theory for solitary waves. So this is a large occupation. There are 200 or 300 mathematicians around the world that work on something like what I'm going to show you in a second. I'm going to take a very simple model problem to talk about, but much more complicated things have been done. Okay, so here's a class of Korteweg-de Vries type equations. So it starts off this ut plus ux. That just says that the waves are basically propagating to the right. And then there's a nonlinear term, and I'm going to just let it be some smooth function. It doesn't have to be u squared. Okay, it could be u cubed, could be, it's typically in real applications, it's a polynomial. Okay, but it doesn't have to be homogeneous. And then I've got this dispersive term, and the L here is what's called a Fourier multiplier operator, which is very simple. It just means that you put L on a function u, you take its Fourier transform in x, and you see what that is, and it's just a multiplication by some symbol, delta of k, times u hat. So that's a Fourier multiplier operator. They come up in harmonic analysis all the time. So if f of z is z squared and delta of k is k squared, you're back to Korteweg-de Vries. Okay, but there's no reason, I mean, other things come up. In particular, other deltas come up. And of course, these will be non-local operators in general. So the question, there's two questions right away. First of all, is the initial value problem for that well posed? Locally, globally. I'm not going to talk about well-posedness theory. This also is a large preoccupation, and we've had probably a dozen lectures or maybe more in this conference on this subject. And these are very, very modern things that are being talked about. They are highly technical, not appropriate for this lecture. So I'm going to leave that stuff aside. I'm going to assume that we have nice, smooth solutions. Okay. Oh, let's see. It's just something to get rid of. This function f, you can assume that f of 0 is 0 because you're differentiating it. So even if it had a constant, the derivative would be 0. You can also assume that f prime of 0 is 0 because otherwise you would put that into this term. Okay? So the function f that we've got here automatically comes with 0 and its derivative, first derivative is 0. We're looking for a solitary, sorry about the typo, solitary wave of speed 1 plus c, with c bigger than 1. You make this traveling wave assumption, you stick it into that little simple-minded equation, and you get this equation. Okay, let's just check. Yeah, the ut, the time derivative, just throws out a 1 plus c, right? And the ux is 1 plus c times phi prime, and the ux throws out a phi prime. The minus 1 and the plus 1 go away, and you're left with this equation. Okay? So it's an ordinary differential equation, but it's not local, right? The operator L is not local. Okay, now again, just as in when we were looking at Airy's theory, everything in sight has a derivative on it. So if you assume that things go to 0, say at infinity, then the constant that would be implied here is 0, and you can take those derivatives off. Okay, so you end up with this equation. All right, and as soon as you see an equation like that, the first reaction of any analyst is to say, okay, fine, C plus L, if that happened to be invertible, I can make this into a fixed point problem. So C plus L inverse, just stick that on both sides, and you'll get C plus L inverse applied to f of phi equals phi. And this thing on the right-hand side, just some operator. You give me a phi, and this will give you something else. And you're looking for a function that operator doesn't move, a fixed point. Okay, so you've turned, goes back to Hilbert and maybe further. You've turned a problem, a differential equation, into a problem of finding a fixed point for this operator A, which is this thing. Okay. So that gives you a step up. You go get your thick book of fixed point theorems, and you say, okay, which one's going to work? And the first one that occurs to you is the contraction mapping principle, Schauder's theorem. There's a bunch of them. And in fact, you can use the contraction mapping theorem for this. But what's the problem? Okay, so I'm now in function space. This is infinite dimensions. And I've got this operator A, and I take a little ball around the origin. And A is contractive in this ball. So it has a fixed point. Unfortunately, that's not interesting because there's an obvious fixed point sitting in front of you, phi equals 0, right? And you don't exclude that by taking a ball around the origin. And it's hard work to try to figure out if the thing would be contractive somewhere else. That you don't seem to be able to get your hands on. So you need a different kind of theorem that would give you a non-zero fixed point. All right, and fortunately there is such a theorem. Yeah, okay. This is something. C plus L inverse is a Fourier multiplier operator with this symbol. It's a simple calculation. And so this is really a convolution equation. The K here, remember the Fourier transform of product is a convolution. The K here is, its Fourier transform is just this symbol. And so this becomes your problem. So and by the way, properties of capital K are easily deduced from this, okay? So all of this seems good. Okay, so here's the theorem that's helpful. This is Krasnozelsky's theorem, one of his many. So now let's see, we have to talk about this a little bit. I've got a cone in a Banach space. 5 minutes, I see. All right, maybe on second thought, we won't go into this. It's a pity because it's fun, but let's go on. So you have to take Krasnozelsky's theorem, you have to generalize it, because one of the hypotheses is that the operator is compact, and convolution on the line is never compact. So you have to generalize it. The way you do that is weaken the topology. See that if you weaken the topology, it's easier for things to be compact. It's harder to be continuous, but it's easier to be compact. So you have to weaken it just enough that the convolution becomes compact, but not so weak that it loses continuity. You can do that. All right, so I won't go into this. This involves, actually it involves degree theory. You're stuck with using degree theory for reasons I won't go into. Okay, there's a stability theory for solitary. The next thing you want to know about solitary waves is, are they stable? Because when you look at them in the world, they are stable. The ones you see are all stable. So you'd like a theory that says that. Here's the kind of result you would like. Let phi be a solitary wave. Let psi be something nearby. So a small perturbation of the solitary wave. Think of putting a stone into the water or something like that. And what you want is that if U is the solution of your model that emanates from psi, then you'd like U to always be close to the solitary wave. And this is not true. It's not true. The reason is very simple. Phi moves at speed c. The psi that you take could be a solitary wave of slightly different speed. They'll be close together, but they propagate at different speeds. So they're going to pull apart as time goes on. So this result's not true. But you could hope that what might be true is that if I moved the perturbation, if I moved the solitary wave at just the right speed, which might vary with time, then maybe I can do it. And this, in fact, you can. And what's nice, this theory started already in the 70s. Benjamin was the first to make a serious contribution. Here's some of the major names. This gets you to about 1987. After that, the number of people is too large. The number of different equations being studied is vast, and I wouldn't attempt to fill out this picture. I won't go into the theory, but, oh, sorry, I do have to. These equations, the ones that we're looking at, have two invariants. One is this. So if U is a solution of the problem, and you compute this is in principle a function of time, but in fact it's constant. It's an invariant of the motion. And so is this one. U, L that dispersive operator, minus 2 times capital F. Capital F is just the integral of little f. Okay? Those are both invariants. And the theory, it's a very nice theorem when you finally finish with it. You take your solitary wave phi, which is a function of time, fix the speed, c naught. You want to know if this is stable. And the answer is, I'm up to some hypotheses I haven't told you. The answer is, if you look at this function, this is a real function of a real variable. And you'd put h on the solitary wave of speed c, plus c times m on the solitary wave of speed c. That's a function of c. It's just a function of c. And if the second derivative of that is positive, it's stable. And by the way, if it's negative, it's unstable. That's a wonderful theorem because it's so easy to apply. So let's apply it. So here's the generalized Korteweg-de Vries equation. Korteweg-de Vries, except that the nonlinearity is higher. Okay, you apply this criterion, and what you'll find is that the solitary wave solutions are all stable for p less than 4, and all unstable if p is greater than or equal to 4. Okay, fine. That's sort of a complete answer to this question, but there's another question that comes up. What happens to an unstable solitary wave? If it's stable, it just sort of goes along looking like a solitary wave. If it's unstable, what happens? Well, actually, we don't know. I mean, this is open, except in p equal 4. Otherwise, we don't know. So let's do some numerical simulations. All right, so here's it's p equal 5. I'm simulating that equation you just saw. I put in a solitary wave, and I can integrate a solitary wave. That's comforting. And now I perturb the solitary wave a little bit, about 1% of its amplitude, and I'm having trouble. My numerical scheme is going crazy, even though I have pretty small space and time steps. What's the problem? Well, for the experts, the Courant-Friedrich-Levy condition is being violated very quickly. You need an adaptive scheme. Okay, so you write a fancy adaptive scheme, and now you can straighten it out, and here's what seems to be happening. Okay, so remember, I just perturbed the solitary wave by the smallest amount. So this begins to look like there might be some singularity forming. All right, so you go to, okay, I tell you what, I'm gonna show you what happened in much more detail. So this is that perturbed solitary wave. Well, there's no information anymore. The thing is up to about 300, but there's no information. So now what I'm going to show you is what's under the finest part of my mesh. The finest part of the mesh, I'm going to show you what's above that. So I'm using a magnifying glass to see what's happening. All right. So here we are. I'm at 10 squared. Now I'm at 10 cubed, 10 to the 4th, 10 to the 5th, 10 to the 6th. We've driven this thing up to 10 to the 10th, actually, though I'm not showing you that. Now this is not the same picture 4 times. This is 4 of those pictures I just showed you. And the amplitude starts at about 25. It goes to 500, 5,000, 10 to the 5th. And what I'm showing you across the bottom goes from 10 to the minus 4 to 10 to the minus 13. So it's pretty clear that this thing is blowing up in finite time. However, we don't have a proof of that. That is an open problem. Okay, I'll quit here, but I do want to show you, that these equations work. So this is the channel I built at Penn State, and I just show you. This is a comparison. I won't tell you what's going on. This is a comparison of the measurements, which are these diamonds, and the predictions of the model, you can see that it's the line that you see just behind it. This is not a very nonlinear one, but this is. This is not too far from breaking. And you see that the agreement is very good here at the first. A secondary crest has been generated by nonlinearity. Here the crest is being propagated at slightly the wrong speed. We know how to fix that, but the point is that one sees the model beginning to break down as it should at this level. My engineering friends, however, said this is fantastic, and they use these models all the time. Okay, and here are certain applications that these models have been used for: tsunamis, rogue waves, coastal engineering. The equations get used all the time. Okay, I'll stop there, although I will show you a picture of a rogue wave. This is a rogue wave in the North Sea approaching a boat. Some idiot is not running but taking pictures, and there's a boat going into the trough of a rogue wave. Okay, there's you wake up in your stateroom and you see that. Rogue waves are serious. They break boats. That's an aircraft carrier. One wave did that. Okay, one can explain the question about rogue waves that we don't really understand. Where do they come from? I mean, these are not like a tsunami. They're in seas that are basically peaceful, and all of a sudden you have a big wave, or maybe two. Where does it come from? Okay, you can get a handle on that with these models. Okay, thank you very much for your attention. Sorry for going over.